you guys have a good weekend? Yeah. What's this Eagles people keep talking about? Sorry, obligatory. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, thank you for the students. Just ask you to bless this class. Help us to glorify you what we do this day, Lord. In your name I pray. Amen. All right, so let me just recap real briefly. So if we have, I use gamma, but you could use R. You know, so R of t, I sometimes use R of t, I sometimes use gamma of t. Anyway, both of these are just the position. These are the position vector, if you like. And so we're, you know, got some curve. And so the position vector just takes you from the origin out to where you are. Then, of course, we defined velocity in a previous lecture. Velocity is dr dt, right? And so that would point something like this, perhaps, right? But more recently, we've introduced the unit tangent, big T, right? Which is, what is that? That's 1 over the magnitude of the velocity times the velocity, right? So this has another name, of course. This is also known as v hat, right? And also, by the way, the magnitude of the velocity, what did we learn? That is, we denote by little v. We also proved that that was the time derivative of the arc length. Annoyingly, yet another notation is used. This is also denoted s dot. So there you go, 4 different symbols for the same animal. This is speed all around. Which is what? Speed. Magnitude of the velocity, right? Anyway, v hat is just a unit vector in the direction of the velocity, so perhaps v hat looks like this. So the next order of business, I defined the unit normal, right? Normal was defined to be 1 over the length of t prime times t prime. And so the unit normal, which I'll try to do in blue here. Some other color. There's a pink. Why not? This guy. That is perpendicular to the velocity. Well, it should be also a unit length, so it's something like that. So it makes right angle to the velocity. It points towards the center of the osculating circle, which fits in there. And then we also defined the, excuse me, the binormal. It's also known as the Frenet normal. The binormal is simply defined to be t cross n. And so that thing is perpendicular to both of them. It's also a unit vector. So for the ones I have pictured on the curve right there, you know, v hat is t. Let's see here. So t crossed into n. So my b is where? It's into the board, right? The binormal. All right. So in addition to these, I'll tell you some things we know. You can prove that dt is s dot kappa, which is for curvature, n. You can prove that dn dt is minus the speed times the curvature times the tangent plus the speed times the torsion times the binormal. And finally, the time rate of change of the binormal is minus the speed times the torsion times the normal. So here's some useful definitions in terms of calculation. The curvature at time t, you can calculate that. It's simply given by 1 over the speed times the magnitude of dt. So this is curvature. And also the torsion at time t we can calculate from the following formula. Essentially, it's our definition, minus 1 over s dot dB dt dot the normal. Now, there are all kinds of specialty formulas you'll find in other calculus textbooks that give you how to calculate these things for like planar curves or in terms of derivatives and third derivatives. There's all kinds of trick formulas which are out there to learn for these things. I don't require you to learn any of those. I just want you to know these definitions, and maybe you can calculate for like a helix or something basic, yeah.
Sorry, did you say the second one was the torsion?
That's the torsion, yeah. Okay, so just a recap. These are the, this is the differential geometry of curves in a nutshell. So what I wanted to do is to try to look at kinematics, try to connect kinematics to this story. Kinematics a la physics 231 here, I'll put a plus on that because 231 is probably a little bit dumbed down from where we are at the moment. Unless they're not following the text. But so first order of business, the velocity, right, is what? It's the speed times v hat, right? So that's a formula we know. It's kind of interesting. Of course, we could also write that that is, for what it's worth, that's also the speed times the unit tangent, right? So the velocity is necessarily in the same direction as the unit tangent. I'm not telling you anything especially surprising. Another thing I should mention, how about distance traveled? How do we define distance traveled? Say integral from t1 to t2 of what? What's that? Yeah, VDT, right. So the distance traveled is not usually the magnitude of the displacement, right? The magnitude of the displacement is through as the crow flies, so to speak, right? Like for a kind of painful example of this, if you go in a circle, right? This is time 2 and this is time 1, right? What's the distance traveled? Well, the distance traveled is about 2 pi r. What's the straight line distance? Yeah, it's 0. So anyway, to integrate, we integrate the speed over the time to find the distance traveled, also known as the arc length. Okay, arc length is distance traveled. All right, so next order of business here would be acceleration. What's acceleration? Well, acceleration is dv dt, right? And so I did this calculation for you guys another day, but let's do it again. So dt dt would be the derivative with respect to time of v times t prime, right? Well, times t. V times the unit tangent. And this is a product rule, right? This is a function of time. That's a function of time, right? So we got to do product rule. What does product rule tell me? Product rule tells me that this is the derivative of the speed with respect to time times the unit tangent plus the speed times dt dt. But this is where the Frenet-Ray equations come into play. See, dt dt, it's not just any old thing. It's related to the normal according to the first. These are, by the way, the Frenet-Ray equations, which we could derive by simple application of the calculus that I've half proved for you, and just dot product arguments. It's not hard to derive these. It's in my notes, Anyway, so we can simplify the derivative of the unit tangent with respect to time to rewrite in terms of speed, curvature, and normal. So this is what? This is equal to the dv dt times t plus what? Plus v times s dot kappa times the unit normal, right? Using the Frenet-Ray equation. Of course, now I've used two different notations for the same thing. What is this actually? So we got dv dt times t. We could rewrite this as what? Just like kappa v squared, right? You guys with me? Now, let's look at this equation. Let's take the dot product of the equation with t. What's a dot t? Let's say that that's a sub t. It's the tangential component to the acceleration, right? But that's also equal to dv dt t dot t, right? Plus kappa v squared n dot t. What's n dot t? It's 0, right? If you forgot, that follows because t dot t equals to 1. So t prime dot t plus t dot t prime equals to 0, which is to say that t prime dot t equals to 0. But the normal vector is just the unit vector in the t prime direction. So of course, it's also perpendicular to t. In case you forgot. That's the argument. But anyway, n dot t is in fact 0. The normal and the unit tangent are perpendicular. What's t dot t? It's 1. All right, so there we go. So we got dv dt. The tangential acceleration is merely the time rate of change of the speed. And then what's the normal component to the acceleration? By nearly the same calculation, I won't even write it down, but a sub n is what? It's going to be equal to the, now n dot, the first term dot product's to 0, and the second term just picks up a kappa v squared. So there's a formula for the normal component to the acceleration. It's just the speed squared times the curvature. For example, we could show, if we have a circle, right, of radius r, we could calculate the curvature for this. Let me do it. Let's see here. So what would the parametric equations of the circle be? How about this? R cosine t, R sine t, and we'll put it in the xy plane for convenience. Yeah. There's a parameterization of a circle, radius r. What's the velocity? Right? I just factored the r out. So what's the unit tangent to the circle? See, I've lost a kind of important thing. What'd I lose? Yeah, this is kind of a bad day at work. You're like, yeah, you know, I went to work and I was three-dimensional, and then something happened, and sorry, I'm horribly deformed. You know, it's kind of like those squirrels you see on the road sometimes, projected into the two-dimensional space. It's kind of the best example I can think of for a projection, really. It's kind of violent, but, you know, true. Anyway, so this is unit tangent. And then to t prime, what's t prime? T prime is, well, it's minus cosine t minus sine t, 0, right? So what's that say the magnitude of t prime is here? Yeah, it's just as already a unit vector is already 1, which implies that the normal vector here is nothing more than t prime. So there's your normal vector, right? This is really hardly surprising if you think about it, right? This is the tangent vector. The normal vector looks like that. The point itself, you know, and then you can even view t geometrically here if you wanted to. I've assumed that the motion is counterclockwise, yeah? Yep.
Where did r go from the velocity vector to t?
Where did r? T is, remember, it's the unit tangent. So we want a vector of length 1 that goes in the velocity direction. What's the length of v? Sorry. That's actually kind of a, I've buried the leader. What's the length of v? It's r, right? So t is v over r. But that's actually important because we need it now. What's the speed? Speed v is equal to r for my parameterization, right? Because that is the magnitude of the velocity. Therefore, what's the curvature? Go back to the definition for it over here. We do 1 over the speed times the magnitude of dt dt, right? 1 over s dot times the magnitude of dt dt, which is a magnitude, well, t prime is just length 1, so this is just 1 over the speed. The curvature, of course, is 1 over r. Just a curvature, it's constant, and it's the reciprocal of the radius. What's the binormal here? I mean, you can calculate it, but it shouldn't be surprising, really. If you point your right hand in the direction of t, cross into n, into the board. Into the board. T, n goes in the middle, into the board. So the binormal is always into the board, into the board, into the board. Work this out, you get what? Zero, zero, then what? Sine squared minus, you get 1. This is a planar curve. It has constant binormal. I mean, you think about the point of application of the binormal moving around, but it always has the same direction, that vector, right? The binormal's, it's always just pointing out of the board, or into the board as my system of coordinates is. It's always pointing into the board no matter where you're looking at. Even though the t and the n are changing direction, they always conspire to make the binormal go in the same direction because this is a planar curve. What's the torsion? Torsion, right, is what? By definition, minus 1 over the speed, which in this case is r, times what? dB dt dot n. But what is dB dt? B is constant, right? So this is 0. So the torsion is 0. So this one's a little bit easier than the helix example I strung out over last class, right? Let's get back to kinematics, though. What I wanted to point out to you guys is the thing we study in Physics 231 a lot is circular motion, right? So for circular motion, the curve, for circular motion, right? For circular motion, we have that the curvature is 1 over the radius, right? So what's my formula for acceleration look like? Acceleration is what? It's dv dt plus times the tangent direction plus what? V squared over r times the normal direction, right? So this general derivation specializes to just this, which of course gives you the formulas that you might remember. The tangential acceleration is the change in the speed with respect to time, whereas the normal acceleration is given by v squared over r, where again v is the speed. Also known as the centripetal or center-seeking acceleration, right? Questions? Let's try to do this for something ugly. I laugh because, you know, you can take a relatively simple curve. I mean, something that you can understand the origin of somewhat simply. You know, for example, imagine you took a donut, right? One of these guys. And then just take another curve and kind of like just wind it around in some sort of sense. Like take a string, you just wind it around a donut. And then calculate the curvature and torsion of such a curve. My brother has an example, or no, I think I did last time when I had a math battle. I gave them an example where it took Mathematica, if I remember right, 280 pages to present the curvature, torsion, and Frenet frame because they're just that awful. Like, it just goes on and on. I mean, so calculationally, these things can be very, very intense. And yet, if I am careful to give you problems that are not too maniacal, you can do them, like circle. Last time we did helix, right? There's another example in my notes here, which isn't too bad. Example 2.21, I do e to the t cosine t, e to the t sine t, e to the t, and I calculate the Frenet frame as well as the curvature and torsion there. I might put that up on the projector screen here in a bit, but let's just try, since we don't know better, let's just, you guys give me a curve and we'll try to calculate the tangential. Oh, whoa, something I'm forgetting here. So, if you're trying to calculate a sub t and a sub n, which of these is easier to calculate? Let's put that in your hopper, mentally speaking, and let's look at an example. I'll try to convince you of something you don't want to do. So here we go. We've got r of t, let's say 1 t squared. Not too bad. Let's try to calculate the tangential and normal components to the acceleration. I think that's pretty much like the last problem in your homework, right? That's the one thing I haven't quite touched on yet in here. Ignoring the problems, of course, which require creative this and that, which I've helped you with if you've come to me for help. Anyway, so first order of business, find the speed. Find the unit tangent. So velocity is what? 0, 1, 2t, right? So what's the speed? The speed is the square root of 1 plus 4t squared, right? So we can calculate the tangent. What's the tangent? It's 1 over the square root of 1 plus 4t squared, 0, 1, 2t. There's my unit tangent. What's the acceleration? How do you calculate acceleration from position? Take the derivative 2 times, right? So it looks like we got 0, 0, 2. This isn't that exciting. Oh, man. I was hoping to have an example at least had something to it. It's not. This one's almost too easy, my luck. What's the tangential and normal components to the acceleration? I guess it's still got something to it. How do you find the tangential component? To find the tangential component, I just take a dot t, right? What's that give me? Looks like 4t over the speed. Right? Now, allegedly, what else should that be equal to? I mean, that was one way we could have done it. What's the other way we could have done it? We supposedly could have also calculated this, or we could have done, yeah, dv dt. What's dv dt here? See this? Chain rule says what? 8t divided by 2 times the square root of 1 plus 4t squared. Hey, well, you know, math works. These are very different calculational paths, are they not? The dot product versus the derivative. Which one's easier for a given problem? I don't know. Now, how about so anyway, we've got the tangential component. How do you find the normal component? Now, the straightforward way, if you just look at my bag of tricks over here, is to take the dot product, it would be to take the dot product with n, right? I mean, it's v squared over r, but what's r? This is for a circle too, right? So more generally, it's kappa v squared. So do we know the curvature for this curve? We do not. So how can we get it here? But here's the thing. Check this out, guys. A sub n is also equal to what? It's equal to the acceleration minus what? This is the sneaky step that I needed to share with you. This is just like finding the orthogonal projection. Once we know the vector, we know the projection, we subtract. So you just subtract the thing we already found. That will be the normal component, right? That's not bad because that's just what? That's just, oh, well, I'm sorry, I need to not cram that into the corner. Check this out. So we have a sub n is equal to what? It's equal to a minus a sub t, which is equal to what? 0, 0, 2. And our a sub t was what? It was the speed, the change in speed per time, which was 4t over the square root of 1 plus 4t squared. And what was my unit tangent, though? See, that's where I got to be careful. 1 over the square root of 1 plus 4t squared, right? Times 0, 1, 2t. What's this work? I mean, what does this give us? 0 in the first component, right? Next time we got ourselves a minus 4t over 1 plus 4t squared. And what's the last one? We've got ourselves a 2, right? Minus, looks like 8t squared divided by 1 plus 4t squared. That's the normal component to the acceleration. You notice that I did not have to calculate curvature to get this. But I would also point out to you that now that you have this, you could calculate the curvature, right? How is the curvature related to the normal acceleration? So down here we have, so a sub n, right, is equal to a sub n dot n, right? That means the dot product of this with n. So let me get more to the point here. Sorry. Not helpful. This is kappa v squared, right? So therefore, the curvature is also equal to what? It's equal to the normal component divided by what? The speed squared. What is a sub n? It's the magnitude of a sub n, right? What is the magnitude of the normal? I mean, this is 1 over the v here was 1 plus 4t squared, right? Square root, but then if I square it, it gets rid of the square root. It's by 1 over v squared. What's the a sub n? A sub n we can calculate as the square root of this. That squared, 16t squared divided by 1 plus 4t squared plus, and I won't even try to simplify it, but you could simplify this. Maybe it would help make it more easier to sell to the correct agency and whatever that would be. But there you go. There is the curvature at time t for this curve. So I just found a sneaky way to calculate curvature without doing it like I said before, right? What's the torsion for this one? You notice the torsion does not enter into the story of kinematics directly, does it? But this problem, you notice something about this? This is actually a planar curve. Can you tell me what plane this curve lies in? If I was to draw this plane right here, it's the x equals 1 plane, right? And this is essentially, I mean, all I did really here was to give you something like it's really just a parabola in the x equals 1 plane with parameter y equal to t, and z equal to t squared. So it's a parabola that opens up like that. But a parabola apparently has kind of complicated curvature function, doesn't it? But that kind of makes sense to you too if you think about it, right? If you think about a parabola, should it have constant curvature? Parabola looks something like that, right? So if you think about the osculating circle down here, it's like that, right? What's the osculating circle like a little bit further up? It's, I don't know, it gets, I mean, the size of the osculating circle clearly varies as we go along the curve, which is why this formula is so complicated, because this should be the reciprocal to the radius of the osculating circle, if you sort through these ideas. All right. Any questions? I hope I've shown you enough that you can do that last homework problem, right? Do you feel confident? If you I give you the path, differentiate once, find the velocity, normalize it. That gives you the unit tangent, right? The magnitude is the speed. Differentiate it one more time. That gives you the acceleration. And then you can take the dot product of the acceleration with the unit tangent. That will tell you the a sub t. Or, if you like, you can just differentiate the speed function. That will give you a sub t. How do you find the normal component to the acceleration? I think the best way to do it is just to subtract the tangential piece off the acceleration. What's left has to be the normal piece. The alternative path is to calculate the unit normal But you really don't want to calculate the unit normal directly here for this one, because it's just a pain. See, because what happens with t prime? See what happens when you calculate n directly? T prime has got a product rule. It doesn't have a nice magnitude. You still got to normalize it. It's just ugly to do it directly. So the path I just showed you is much easier for this problem. Okay, anyway, let me, I think that's all I got for lecture today. Let me give you the daily quiz now. You can stop recording for the moment.